Okay, guys. Now we're doing problem 4, example 1. So this is like the second page on the second day. So it says Mr. Pierce shoots a Nerf dart straight up. The dart takes 4 seconds to go up and down and come down to the level of the gun. Ignore air resistance. So when you guys get to this problem, it's going to be a really good idea to just go ahead and draw a picture because it's going to be confusing if you don't draw a picture. So I'm going to zoom in a little bit here, and I'm going to draw Mr. Pierce. Okay, looking good. And he's got his little Nerf dart gun. I don't know if that looks like a Nerf dart gun. That's confusing. All right, we're just going to pretend he's got a gun in his hand there. And he's going to shoot a Nerf dart, and it's going to go straight up, and then it's going to go straight back down. Now notice that I only drew the arrow down to the level of his hand. So the problem says that it comes down to the level of the gun. And so the reason that I do this is if we talk about the dart going all the way to the floor, that makes it more complicated. So we just talked about going up and then back down to the place it started from. And I know that it's going to take 4 seconds. So from let's do a different color. From here all the way up and all the way down, that's going to take 4 seconds. Now, here's the thing that we have to sort of get in our mind, is that the whole time up and down is never very useful to us. So what we really want to look at is how long does it take just to go up? So just to start off at his hand and get up to its highest point. And remember that it takes the same amount of time to go up as it does to go down. So really, 2 is going to be a more useful number here for us, because that's the time that it takes just to go to its highest point. So now let's talk about what we know here. So they tell me that it's 4 seconds to go up and down. So 2 is my delta t. Delta t just for going to the top. And we're going to see why it's really important for us to know just going to the top, because what we're talking about is this section of the motion right here. We don't even care that it comes back down. All we're wondering about is this section of the motion. And so there's going to be a velocity at the beginning, and there's also going to be a velocity at the end. Now, we don't know the velocity at the beginning yet, and they're actually asking for that velocity, but we do know the velocity at the end, because the velocity at the highest point is always equal to 0. So now I know delta t, I know Vf, and this is asking for initial velocity, so Vi becomes my question mark. So now I have enough to use the first equation. I have enough to use this equation right here. Vf equals Vi minus 9.8 delta t. Now, pay close attention. This is not a delta t squared. It's just a delta t. But now I can plug in. My 2 goes in there. My 0 goes in there. So I've got 0 equals Vi minus 9.8 times 2. And 9.8 times 2 is 19.6. So 0 equals Vi minus 19.6. Now, Vi is still not by itself, so I need to do a little bit of algebra to get it by itself. Since I'm subtracting negative 19.6, I want to do the opposite of that to get rid of it. And I want to add 19.6 on both sides. So I'm going to end up with Vi equals 19.6 meters per second. Don't forget your units. Write it on your card. Don't forget your flipping units. Okay, so distance the dart travels from the barrel of the gun to its highest point. Okay, so again, I know delta t, because we're talking about highest point, is 2. I know Vf is 0. I know Vi is 19.6. And what am I looking for? I'm looking for highest point. Sounds an awful lot like Y max to me. So Y max is my question mark. So remember that Y max equals 4.9 delta t squared. So now all I have to do is plug in. So delta t is really all I need here. So I don't need that, don't need that. I'm using delta t, y max equals 4.9 times 2 squared. 2 squared is 4. 4.9 times 4 is 19.6. That's interesting. Huh. 19.6 meters. Now, let me say this, people. The fact that these two are the same is what we call a total coincidence. There is no significance to those two numbers being the same. It is a total coincidence. Don't read too much into that. Okay, now finally we want to draw the graphs. So position versus time. So remember that I'm going to start down here at 0, and the dart's going to go up, and then it's gradually going to get less and less steep because it's slowing down. And it's going to get to a point where it reaches its max, and then it's going to get more and more steep as it goes down. So I showed it with this nice curve. And actually, that mine's not quite symmetrical. Yours, here, we'll draw it symmetrical. Like, there we go. Should be closer to symmetrical. So it curves up and then curves down. Now, velocity versus time. Okay, so this one's interesting because I start off with positive velocity, right? So I start off with a velocity of 19.6. Well, it's going to go all the way up, and it's going to slow down. So if I start off up here, around 19.6, it's going to slow down all the way to 0. Remember, this is 0. Now, after it slows down, it's going to keep on going and speed back up. So remember that this section up here is on the way up. This section down here is on the way down. And the top part is slowing down, the bottom part is speeding up. You guys, by the way, you guys don't need to draw in all that stuff. If you just have the line, you're good. Now, acceleration versus time must include numbers. Acceleration, guys, acceleration due to gravity is always the same. It's written in the top left-hand corner of the board right now while you're working on this, and it is always, always negative 9.8. As long as you label negative 9.8, I am totally good on this. It's flat. It doesn't change. It's negative 9.8. It's super easy. Okay, guys, there we go. Try the next one on your own.